We've talked about the definition of a basis, and we said that a basis is a set that both is linearly independent and spans a vector space. So now we're going to talk about the representation of a vector in that vector space. And it turns out that representation for that particular basis is going to be a unique representation, which means there's going to be only one way to represent it. So let's say we have a basis set S, so it's got V1, V2, all the way up to Vn actors. This forms a basis for our vector space V. What that means is every vector in V can be written in one and only one way, as a linear combination of all those vectors in S. So that's a pretty powerful theorem. What that's saying is that there's only one way each vector in that vector space can be expressed as a linear combination. So let's look at example 6. This is going to be a very generic example, and then we'll make it more specific. Let's let U be any vector in R3, and we want to show that this vector, U, notice this is a very generic vector because of the C1s, C2s, and C3s, can be written as a linear combination of these vectors. I'm going to call this first one V1, V2, and V3, like the book has done here. So what's your notation? So let's work this out. The first thing we want to do is set up our linear system. So we have C1, C2, and C3. Just kidding. We have U1, U2, and U3. That's the vector, if you remember back here. There's our generic vector that we're going to write as a linear combination of those vectors. So U is equal to C1 times the first vector plus C2 times the second vector plus C3 times the third vector. That's going to allow us to create our system. So when I see this system, and I know I want to solve it, remember the goal is to solve for C1, C2, and C3. That's what we're looking for. Those are actually called coordinates for that vector. We can solve this more easily by thinking about this in terms of AX equals B. So here our coefficient matrix is this 0, 1, 0, negative 2, 2, 1, 0, 3, 2, 1. Our X matrix are the coordinates that we're looking for, C1, C2, and C3. And our B matrix is the vector we're trying to express, U1, U2, and U3. So to solve something for AX equals B, we can multiply by the inverse of A on the left. So X equals A inverse times B. Now we know this guy's going to be invertible because this is a basis. So there will be a unique solution to this. So to find A inverse, we're just going to pop this guy in the calculator. We could work this out by hand, but by now we've done that enough to where we can save a little time and use some technology. So if we plug that into the calculator, here's what I got. Negative 1, 4, negative 2, 2, negative 7, 4, negative 1, 2, negative 1. So now our C1, C2, C3 is equal to A inverse times our U1, U2, U3. So let's multiply these together. So there's what C1, C2, and C3 have to be. So notice we've got an equation essentially for C1, C2, and C3. And that's because our U vector, the vector we're trying to express, started out being a very generic vector. So let's kind of take this and put it to the test. Suppose now that we know we have formulas for every vector in U, suppose we want to write a specific vector. Let's do the vector 1, 1, 1 as a linear combination of those vectors from S, which we had to begin with. So we're talking about going back. We're now writing 1, 1, 1 as a linear combination of these. Sure, we could go through and we could put 1, 1 here and then solve that system. But we've done all of this work. Let's use that formula that we came up with here. So our C1 should be negative U1 plus 4 times U2 minus 2 times U3. So negative 1 plus 4 minus 2 is a 1. C2 should be 2 times U1 minus 7 times U2 plus 4 times U3. So 2 minus 7 plus 4, and then C3. Negative U1 plus 2 times U2 minus U3, 0. So here's what we're saying. We're saying we can write 1, 1, 1 as a linear combination of the vectors 1, 2, 3, 0, 1, 2, and negative 2, 0, 1. And our coordinates are 1 times the first vector minus 1 times the second vector plus 0 times the third vector. Now, if you were to multiply all this out, you will get this guy back. So that generic form is nice because if you had to do a lot of these, if we had to write maybe 10 different vectors in R3 as a linear combination of those, then we could just pop all of those guys into this formula and call it a day. That's why that's nice. So let's look through example 7 and discuss what's going on here. A is looking at R3. So when we talk about R3, we're talking about vectors that are in 3 dimensions. To have a basis for R3, you only have to have 3 vectors. So anything else would give us a dependent set. So because this set here has 1, 2, 3, 4 vectors, then this must be a dependent set, which means that one of those vectors can be written as a combination of the other vectors. So if you think about how many you have to have for a basis, R3 has to have 3 vectors. R2 has to have 2. R4 would have to have 4, and so on. So you can start to see that connection there. How many vectors do I have to have, and how many vectors do I have? So if you think about P3 is a set of polynomials that are degree 3 or yet less. So there's your polynomials. So your standard basis for P3 would consist of the constant 1, x squared, and x cubed. So for P3, you have to have 4 vectors. So let's look at this scenario in part B. Since you have to have 4 vectors in P3, then this set has to be dependent. Why does it have to be dependent? Well, let's look at how many vectors we have. We have 1, 2, 3, 4, 5. So right off the bat, we have too many vectors. If you know you only need 4 and you have more vectors than what you need, then you know that there has to be a dependent vector in there. So that set must be dependent. And if it's dependent, then it can never form a basis. Theorem 4.11 talks about how many vectors do you need to form that basis. So if we have a vector space V that has a basis with n vectors, then that means every basis for V has to have n vectors. So it kind of goes back to what we were talking about with R3 up here. We know the standard vectors are I, J, and K for R3. Because that basis has 3 vectors in it, then that means any basis we could form for R3 would have to have exactly 3 vectors. No more and no less. B is the same way. Because we know that standard basis here consists of 4 vectors for P3, then that means every basis we could come up with will have to have exactly 4 vectors for P3. So if you know something about the vector space to begin with, and you know one basis in that vector space, and the one you know will generally be your standard basis, then that means that means you know something about every vector space. Excuse me, not every vector space. You know something about every basis for that particular vector space, and that they all have to have the same number of vectors. So let's use those ideas to look at example 8. And A is talking about the set that consists of these 2 vectors. I'll call them V1 and V2. And they're asking you to explain why this is not a basis for R3. Well, we know R3 must have 3 vectors. And since we have to have 3 vectors, but they've only given us 2 in this set, then there's no way this guy could be a basis for R3. Same kind of scenario for part B. They're giving us 1, 2, 3, 4, 5 vectors. But we know for P3, going back, P3 has to have 1, 2, 3, 4 vectors to span and to be a basis. So what this means is that we have 1 vector too many, so one of these is a linear combination of the other ones. We only need 4 vectors to form a basis in P3. Now, we can't just pick one and say this one's the one that's the issue. We would have to go through and say, can I write this guy as a linear combination of the other ones? Can I write this one as a linear combination? And figure out, by elimination, really, which one would be the culprit. And my guess would be that I could write this one or this one. I could pick either one as a linear combinations of the other ones. We have to have x cubed. We have to have x squareds. I could probably write that one. Or possibly even that one. So that's how you would go about maybe trying to eliminate. So just so you can see that, let's go through and do that. So we know this guy's a problem, right? We have 2 main vectors. One of them has to be a linear combination. I'm going to guess that this one is. And that's a pure guess. So let's see if we're going to get it to work out. This is example 8, part B. We have too many vectors. So let's see if we can write 3x plus 1 as a linear combination of x plus 2, x squared, x cubed minus 1, and x squared minus 2x plus 3. So we're going to set up our system. Remember, we have x cubes, x squareds, x's, and constants. 0x cubed on the left is equal to c3. 0x squared on the left is equal to c2 minus 2c4. Oh, just kidding. I'm looking at squareds, so plus c4. X's, I have 3, is equal to c1 minus 2c4. And then constants, I have 1 on the left, is equal to 2c1 minus c3 plus 3c4. So if we were to plug that into our system and do RREF, I'm going to get the identity on the left. And here's what I get. So the answer is yes. We could write 3x plus 1 as a linear combination of those four. So what that's saying is that this vector poses a problem. Now, if we were to take that out, then we may have a basis. We still have to go through and check spanning and check linear independence, but at least that gives us the 4 vectors that we potentially need. So that one's definitely a linear combination. The next thing we need to talk about is the definition of a dimension. And the dimension is really how many vectors you have to form a basis for that vector space. Now, the special vector space that consists of just the 0 vector, the dimension of that is defined by 0. So if we're talking about the dimension for R3, we've talked about R3 a lot in the last few. The dimension of R3 is going to be 3 because you have to have 3 vectors to span. The dimension of R2 is 2 because you got to have 2 vectors to span and they have to be linearly independent. So you got to have 2 to form a basis. In R2, 3 in R3, which means in Rn, you got to have n. Now, with polynomials, it's a little bit different. Notice for P3 up here, we had to have 4. So for Pn, you got to have n plus 1. So P3 had to have 4 vectors, so that was a dimension 4 space. P2 has to have 3. And your standard set is 1x and x squared. So P5 would have to have 6, and so on. When we talk about matrices, any matrix of dimensions m by n, then you have to have m times n vectors to form that basis. So M22 is one we talked about before. You have to have 4. So if I wanted M32, the dimension would be 6. So the dimension is really coming from what's that simplest vector, what's the simplest basis that would span that set, that vector space. I think that's probably the easiest way to think about these. So for M22, it was that set that we saw on the other page up here. Okay, notice we had a 1 in the top left, zeros everywhere else. 1 in the top right, zeros everywhere else. 1 in the bottom left, zeros everywhere else. 1 on the bottom right, zeros everywhere else. So that was that simplest vector, a set of vectors that can form any vector in M22. So we're kind of taking that idea of IJK, where I had just that 1 in that first slot, J had a 1 in the second slot, and then K had the 1 in the third slot. And we're kind of expanding this out to polynomials, to matrices, and so on. So you got to think about, what does that look like? So we've talked about vectors in vector spaces. Now let's talk about the dimension of a subspace. So here's the way I like to think about these. We want to think about this subspace where we have vectors that can be written in this form. And C and D are real numbers. So that's what our sets look like here. So I'm going to kind of undo some scalar multiplication here. See if we can pull some stuff out. So we could rewrite this vector as D, negative D, and 0 plus 0, C, C. So would you agree that if we were to add those two together, we would get back what everything looks like in this space? And now, so what I did is I grouped all the D stuff together and I grouped all the C stuff together. So now if I were to factor that D out and then factor that C out, so our basis vectors can't have variables in it. So this guy would be a basis vector and this guy would be a basis vector. So our basis, I'm going to call it B, would be the vector 1, negative 1, 0, and the vector 0, 1, 1. And any vector in this space could be written as a linear combination of those two. So you're kind of undoing that linear combination. So what that means is that the dimension of this vector space is 2, because you have to have 2 vectors in that vector space to span every atom in the space. Now let's look at B. So now our vector space, W, is going to have vectors that look like this. 2B, B, and then 0. And B is just some real number. So let's undo, kind of pull apart what this looks like. So our vectors are 2B, B, and 0. So notice I only have one variable in there. And if I pull that variable out, all my vectors are really a scalar multiple of this vector 2, 1, 0. So my basis here only has one vector in it. So then we would say that the dimension of W in this case is 1.